Welcome to AI Paper Slop. We are jumping straight into it today with a massive paper called Vector Policy Optimization, or VPO.
Right. The full title is Training for Diversity Improves Test Time Search.
Yeah, and this is from Ryan Bolles-Boldy and a collaborative team spanning MIT, the Improbable AI Lab, and Sakana AI.
And it is a fundamental paradigm shift for post-training.
It really is. So here is the core insight you need to know right off the bat. AI systems today are increasingly relying on inference time search, things like AlphaVolve or Best of N, to solve really hard problems.
Right. You generate a bunch of candidates and search for the best one.
Exactly. But standard RL post-training algorithms, like GRPO, they optimize a single scalar reward, and that causes models to suffer from mode collapse.
They just generate the exact same safe answer over and over again.
Which completely starves your search algorithm of the diverse options it actually needs to work. So this paper introduces VPO, which treats rewards as vectors, and explicitly trains the model to generate a diverse set of solutions spanning the Pareto frontier.
It explicitly separates exploration, which happens during training, from exploitation, which your surf handles at test time.
Which unlocks just massive gains in test time scaling. So to really grasp why VPO is such a breakthrough, we probably need to look at what exactly goes wrong with current state-of-the-art RL methods.
Yeah, we should unpack the mechanics of that bottleneck. Because we've spent, the last few years forcing our training algorithms to do the impossible.
Finding the single global optimum.
Right, and then collapsing all the probability mass right onto it. But if you have a multi-objective task, standard RL just ruins your diversity.
Like, say you need a Python script that has to be functionally correct, memory efficient, and readable.
Exactly. Standard RL takes those three totally distinct reward dimensions and just flattens them into a single scalar number. Usually it's just a weighted sum.
Okay, and then policy gradient methods like GRPO step in.
Oh, they are brutally unforgiving when optimizing that scalar. GRPO doesn't care about the nuance of how a model arrived at, say, a score of 0.8.
Right.
It just updates the weights to maximize the likelihood of that specific trajectory. So as training goes on, the model's output distribution sharpens aggressively.
It just zeroes in on that one average path.
Yeah. So any candidate that experiments with like a highly novel memory-efficient approach, but maybe loses a tiny bit on readability, it gets punished by the gradient.
Wow. So the diversity you actually need for test time search is actively trained out of the network.
Completely trained out. You ask for 30 samples at test time, you pay the inference compute for 30 samples, and you basically just receive 30 near-identical variations of the same local maximum.
It's like hiring a team of 10 identical clones who are all just pretty good at everything, instead of hiring 10 diverse specialists who each excel at something different.
That's exactly what it's like.
But wait, I want to push back on this on behalf of the engineers listening. Because if we know exactly what the deployment objective is, like we know the final metric, why shouldn't we just optimize the model to output the absolute best answer for that specific objective?
I mean, that makes sense intuitively, right?
Right. Like, why keep suboptimal answers around at all?
Well, because that assumes you can actually reach the global optimum in a single autoregressive shot.
Okay.
And for highly complex reasoning tasks, that is rarely true. Search algorithms, especially evolutionary ones, operate on sets of candidates.
They need a pool to work with.
Exactly. So a response might score poorly on your final scalar metric. Maybe it completely hallucinates a variable name at the very end of the script.
But early on.
Right. Early in its chain of thought, it might contain a highly unique reasoning pattern or a novel task decomposition.
So it possesses this critical piece of the puzzle that the safe, average clone answer completely missed.
Precisely. In evolutionary search, that unique, locally suboptimal response is your raw genetic material.
Wow.
The search algorithm can grab that novel decomposition, cross-pollinate it with the syntax of a more reliable candidate, and mutate it to reach a vastly superior final solution.
But if you collapsed everything during training,
then you prematurely kill off those alternative strategies. Your evolutionary search has absolutely nothing to evolve. It just spins its wheels, mutating identical clones.
okay, that sets up the problem perfectly. Scalar optimization actively destroys the search space. So how does VPO actually fix this? How does it incentivize reward diversity?
So the paper outlines two core structural components. The first one is multi-answer chains.
Which is taking advantage of the autoregressive nature of LLMs, right?
Yeah, it's a really clever use of the context window. Instead of running multiple independent rollouts where the model has no idea what it just generated in the other runs, VPO trains the model to generate all M-candidate completions sequentially within a single rollout.
Meaning if we want a budget of 3 answers, the model generates answer 1, outputs a delimiter token, generates answer 2, another delimiter, and then answer 3.
Exactly. And because it's all in one massive context window, the attention heads can literally attend to the previous attempts.
It allows for in-context exploration.
Right. The model can look back and say, okay, my first attempt used a really memory-heavy array. Let me try a streaming generator approach for answer 2.
It can actively steer away from its own past distribution.
It can, but having the capacity to steer away is not the same as having the mathematical incentive to actually do it.
Right, because this was a huge point in the paper. Multi-answer generation alone doesn't work.
Not at all.
The researchers tested this baseline called multi-RLVR. It used the exact same multi-answer chain format, but it evaluated the set using a fixed scalar reward, and the diversity completely collapsed.
Yeah, and the gradient mechanics explain exactly why that happens.
Because the landscape doesn't change.
Exactly. If you evaluate a multi-answer chain with fixed scalar weights, the optimization landscape still only has one single peak.
Oh, I see.
So the gradient simply updates the network parameters so that every single slot in that multi-answer chain climbs toward that exact same peak.
It learns the easiest way to get reward is just outputting 3 identical copies of the best scalar answer.
Right, the clones again. So to actually force the model to diverge, you need the second component, which is stochastic scalarization.
This is the secret sauce of the whole paper.
It really is.
Because instead of a fixed reward weight, like 50% correctness and 50% speed, VPO samples weights randomly for each rollout.
They pull weights sampled from a Dirichlet distribution with an alpha of 1.
Which, for people who haven't looked at the math recently.
Yeah, it basically means you are sampling vectors uniformly from a simplex. The weights will always sum to 1, but the distribution across the dimensions varies wildly.
So on one training step, the objective might heavily prioritize readability.
Right, and on the very next batch, that readability weight might drop to near 0, and suddenly execution speed is the only thing that matters.
And the multi-answer chain gets evaluated based on the maximum scalarized reward achieved by any single answer in the set under that random weighting.
That is the critical mechanism.
It makes me think of training a team of athletes for a decathlon.
Oh, that's a good analogy.
Yeah, but you shift the scoring weights randomly every single day of practice. Standard RL trains one athlete to get a safe, mediocre score in all 10 events.
Right.
But under VPO, the model can't cheat by memorizing one perfect trade-off because the objective just keeps moving.
Exactly. The only way to consistently get a high score across all those training steps is to treat the multi-answer chain as a coverage problem.
A coverage problem over the Pareto frontier.
Yes. The network is essentially forced to produce a dedicated sprinter, a dedicated swimmer, and a dedicated weightlifter.
So no matter what random Dirichlet weights are drawn for that batch, one of the specialists in the set will score highly.
And that specialist pulls the gradient up for the entire chain. You are mathematically forcing the model's representations to fan out across the Pareto frontier.
It explicitly trains the model to anticipate diverse downstream reward functions.
Which ensures your test time search always has a high-quality specialist to start from.
Okay, so the elegant math makes complete sense. But, as engineers, we know theory doesn't always survive contact with real data sets.
It rarely does.
So let's get into the empirical evidence. They started with a synthetic maze environment, right? A controlled test bed.
Yeah, it's a synthetic 90 by 90 grid navigation task. The model has to output a path to the exit while collecting gold and diamonds and avoiding lava.
And the geometry is what makes it interesting.
Right. The researchers artificially constrained the step budget. The geometry physically guarantees that no single route can hit all the gold, collect all the diamonds, and still reach the exit in time.
So it forces a strict trade-off. It forces a Pareto frontier.
Exactly. Standard GRPO looks at this forced trade-off and learns a compromise path. It grabs a little gold, maybe a few diamonds, and rushes to the exit.
It finds a local maximum and just stays there.
Yeah, it gets stuck. VPO, on the other hand, learns to use its multi-answer chain to fully explore the state space.
Oh, wow.
One answer in the chain learns a route sweeping the entire left side for gold. Another sweeps the right side for diamonds.
So when you apply a best-at-K search at test time,
VPO's diverse candidate pool allows the search to find solutions with vastly higher total rewards than the Scalar model could ever reach.
okay, so it works on synthetic mazes. What about natural language? They tested on music, right?
Yeah, music for multi-hop reading comprehension, and GRQA for 5-hop logic reasoning.
And VPO outscaled the baselines on best at K as the candidate budget grew.
Right, because in multi-hop reasoning, diversity is critical. A single hallucinated entity early in the chain ruins the whole final answer.
The baselines just keep generating the same flawed logical path.
Exactly, they plateau. But VPO scales continuously.
I really want to dig into the ToolRL benchmark, though, because function calling is where a lot of our listeners live.
Oh yeah, ToolRL is fascinating here.
Because the components are graded by difficulty, right?
Yeah.
Generate the JSON format is easy, the tool name is harder, the keys are harder, and the exact values are the hardest.
Right.
So how does a trade-off actually work when an AI is trying to format a JSON function call? Like, what is the Pareto frontier in function calling?
It's a really crucial distinction. In function calling, the trade-off is almost always between syntax safety and functional ambition.
Interesting.
A model optimizing a single scalar reward will usually play it safe. It outputs a simple, perfectly formatted JSON for a basic tool call because it knows it will secure that format reward.
It completely avoids the risk of a syntax error.
Right, even if it fails to use the advanced nested tools required to actually solve the prompt. But VPO generates a coverage set.
So one candidate plays it safe for the format reward.
And another candidate in the same chain attempts a highly complex nested tool call that addresses the deepest part of the prompt.
Oh, I see.
Now, that complex candidate might drop a bracket and fail the syntax check during training, but at inference time, your search algorithm, like a code execution loop,
It can just take that functionally ambitious candidate and easily fix the syntax error.
exactly. Because VPO provided the complex logical structure, the search algorithm can succeed. The Scalar model never even attempted the complex call.
That is huge. But wait, I have to play the skeptic here for a second.
Go for it.
VPO is generating multiple answers per rollout, and it's evaluating multiple reward dimensions. What if VPO just wins because it's using massively more compute during training?
That is a massive potential confounder.
Are we just brute forcing a better model with extra FLOPs and calling it diversity?
The researchers anticipated that exact question. They ran a rigorous ablation study on the music dataset where they took the baselines, standard GRPO and GDPO, and gave them 3 times the training rollouts.
Oh, cool.
This perfectly matched the language model compute, the token generation counts, and the evaluator calls used by VPO.
So the compute budget was totally normalized.
Completely normalized. And even with 3 times the compute, the scalar baseline still lost to VTO.
That's incredible.
It's definitive proof. If your objective function collapses the probability mass, throwing more training compute at the problem just sharpens that collapse.
So the performance gains really do come structurally from the set-level diversity objective.
Exactly, not just an artifact of extra compute.
Okay, so the ablation holds up. Beating baselines on isolated benchmarks is great, but let's talk about scaling this to genuinely hard problems.
Real-world coding tasks.
Right, paired with heavy-duty evolutionary search. They did a case study on Live Code Bench using Qwen 2.5 Coder 7b, right?
Yeah, and Live Code Bench is the gold standard because it uses a strict temporal held-out cut. It totally rules out data contamination.
But looking at those results, I want to highlight a seemingly glaring negative finding. VPO actually loses to GRPO on single-shot pass at 1.
It does.
So if I don't have time to do a search, doesn't this mean VPO degrades the base capability of the model?
It does, but we have to understand this is an intentional design choice.
Yeah.
It is not a bug.
Okay. How
VPO explicitly trains for exploration at the cost of immediate exploitation. If you only have a budget of 1 sample, standard scalar RL, which trains exclusively for exploitation, will naturally win.
Because it always guesses the safest average path.
Right. VPO is deliberately sacrificing pass at 1 to flatten the distribution and build a wider candidate pool. But when you give it a budget of candidates, when you evaluate best at K, VPO quickly overtakes GRPO.
And the real mic drop moment in the paper is with OpenEvolve.
Oh, absolutely.
OpenEvolve is an evolutionary test time search loop. They ran this on the 32 hardest problems in the set.
Problems so complex that standard GRPO solved exactly 0 of them, even at best at 30.
Wow.
The Scalar model was totally stuck, but when they plugged VPO into OpenEvolve and let it run for 200 iterations,
And actually cracked them.
it continuously discovered new solutions. It cracked open problems the Scalar model literally couldn't touch.
Because GRPO's initial pool was just 30 clones with the same flaws.
Right. The crossover and mutation operations had no novel genetic material to work with. but VPO provided distinct algorithmic approaches.
And it provided the raw genetic material for artificial evolution.
Exactly.
That is just wild. But to give our listeners a complete, rigorous picture, we do have to pivot to the limitations.
Yeah, we have to look at when you should definitely not use VPO.
Right. So I'm looking at the ultra feedback data set, which they evaluated with the Armor M5 reward model. And here, VPO actually failed to beat Scalar GRPO on absolute best at K.
Yeah, and this reveals the underlying mathematics of the method. The problem here is reward collinearity.
Collinearity.
Right, so VPO relies on the premise that different reward dimensions actually trade off against one another, like sacrificing speed for readability.
But in ultra feedback.
In that specific domain, the 5 supposedly distinct reward components from the Armor M model were highly correlated under the trained policy.
Meaning if a response is good at one thing, it's just good at everything.
Exactly. If you calculate the covariance matrix of those rewards, the rank is essentially 1.
Oh, wow.
The Pareto frontier isn't a wide curve of trade-offs anymore. It mathematically collapses into a near straight line.
There's no spread.
Right. And when there are no genuine trade-offs to explore, there are no specialists to train. VPO effectively reduces back to standard RL, and its advantages just disappear.
So if you don't have a true Pareto frontier in your reward model, don't use this.
Exactly.
But if you do have competing objectives, which, let's be real, almost all complex real-world tasks do, the paradigm shift here is massive.
It completely reframes the pipeline. As inference time search becomes standardized, we really have to stop asking training algorithms to handle both exploration and exploitation.
You need to separate them.
Post-training should just build a diverse candidate pool. Test time compute should find the winner.
I love that. And that actually leaves me with a broader industry question for you to ponder as you are building your next system.
Let's hear it.
If test time compute is truly the next frontier of scaling laws, does this mean the era of training these massive Oracle foundation models that are supposed to output the one single perfect answer on the first try, is that era fundamentally over?
That is the question, isn't it?
Could the future of LLMs look much more like generators of diverse possibilities, where the neural network actually requires an external search algorithm to become intelligent?
The model is just the brainstorming session.
Exactly. Something to think about the next time you are tuning a reward function. Thanks for joining us for this deep dive on AI Paperslop. See you next time.